Good afternoon, everyone. Welcome back to the lecture of the course on design and analysis of algorithms. In today's, this is as per the course planner, it is supposed to be lecture number 23. So, in today's lecture, we want to discuss about flow network. And in today's lecture, while discussing about flow network, first we shall understand what do we mean by a flow network. That means a concept of flow in a graph, which is a directed graph. And then um, there are some conditions to be satisfied in a flow network. We shall address them. Okay, and after that we will understand a concept of residual network. Okay, so and after getting understood about the residual network, we then discuss about an augmenting path concept. The augmenting path concept is sort of an approach to applied on a flow network to produce an optimal flow. That means optimal flow means it may be a maximization problem or minimization problem, but in this case it's a maximization problem where our primary motive is to maximize the amount of flow along a path from a source vertex to destination vertex. Okay, and after that we will talk about an application which we have already seen in yesterday's class, that is image segmentation using minimum spanning tree. Okay, so in image segmentation problem, uh, after constructing the minimum spanning tree by representing from the graph representing the digital image, we have to apply some partitioning algorithm onto the minimum spanning tree to produce suboptimal subtrees of that minimum spanning tree. And each of those suboptimal spanning trees actually represent different object present in that digital image. So the question is, what will be the partitioning algorithm? There are many, and one of them is uh, based on this flow network. So you can introduce a cart such that the flow can be maximum or the cart can be minimum. So if you can introduce a cart which is building a maximum flow from source to destination vertex, okay, that could be a useful technique to partition a minimum spanning tree into suboptimal subtrees representing distinct objects present in a digital image. So that is an application. And once we get into that, so we in that application, once we get into that application, we will understand and we will convince ourselves there is a relation between a minimum cut and a maximum flow. And of course, there is a relation, and based on that relation, we will discuss next about a very popular algorithm which is known as max flow mean cut algorithm, and which is actually widely used in image segmentation, image registration, etc. problems in digital image processing. Okay. Okay, so we have two terms to understand first. One of them is a flow, another is a network. So flow in a network. So let's understand first a network. So it's nothing but a directed graph. Let's say is denoted by G equal to uh, V comma E. E is the set of edges in that graph, and V is the set of vertices in that graph G. So where that means it's a combination of a set of vertices and a set of edges. So represented by graph G, such that each of the edge, let's say the one of the edge, any edge is represented by U comma V in that set edge set E, and each of these edge will carries a capacity. So we will now talk about what is a capacity. The capacity of an edge is denoted by small c of u comma v, and it is supposed to be greater than or equal to 0. Okay. Now, uh, capacity of an edge may represent some, let's say, for example, you can think of an electric network. Okay, so in an you can represent an electric network in terms of a graph, or in electric network you know that there are several nodes, so you can think electric network as a graph where there are distinct nodes, and branches are actually the edges connecting the adjacent nodes. So from one node to another node, let's say this is, right. So this is let's say here I'm actually applying, this is grounded, and here you are applying some voltage. Okay, here you are some applying input voltage. So this is, let's say, node number one. Okay, or yeah, in this case it's not required anyway. Okay, 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 it's not required in this case, let's remove it. It is not a distinct node. Fine. So we can have a two node. This is one distinct node, this is another distinct node. So any node if you provide over here, that will have the same potential which is appearing by this positive terminal of the DC voltage source. Okay, so everywhere in this node, if you consider any point, same potential appears, which is equal to the plus. And then here some different voltage is actually present at this terminal, so it's a distinct node, and another node you can see over here. Okay, or you can think that okay, you can introduce a node over here of which voltage is this plus, so you can in that way you can think. So let's say this is another node, this is another node, and this is another. And if you just in impedance form, if you want to redraw this circuit, so it will be like, right. So that is the case. So if you convert this into an impedance form circuit block diagram, it will be like this, where these are nodes and these are impedances. Okay, so this is the branch. So this is the branch, and this can be thought of as an edge. So this is an edge, E, and these are actually nodes. That means these are vertices, small v. Okay, so then you can draw a graph like this and connect them with edges. Okay, so this is vertex number 1, this is vertex number 2, and this is vertex number 3. And the edges, which are nothing but representing the branches, should be assigned some value, some real quantity, and that may denote an impedance, that may denote an admittance, or any other suitable parameter. Okay, so Now here it is supposed to be a directed graph because of the direction of the current flowing into the network. Okay, so here you know that the current flows from 1 to 2 and then 2 to 3 and ultimately to the ground. Okay, so now you can think like, okay, what is the current flowing through this branch and what is the current flowing through this branch. Okay, so current is equivalent to like a flow because the current in series combination, the current should be same throughout all the branches, right? Okay, so it is equivalent to a flow. And capacity is some sort of a restriction in a branch. That means no, that means capacity is actually equivalent to the impedance. For example, if I provide an impedance, so as per the impedance, a current will flow in that along that branch. Okay, so minimum impedance will yield highest current flowing through that branch, and maximum impedance is resulting in minimum current flowing into that along that branch. So there is a range of impedances, and consequently there will be a range of currents. So minimum current, maximum current. So that means there is a concept of a maximum current by introducing a minimum possible impedance in a branch, right? So what is the maximum current? That means what is the minimum impedance? So maximum current, or I mean, is actually you can think you can think that maximum current is equivalent to that capacity. Flowing along a branch is equivalent to the capacity of a of an edge. Okay, and actual current flowing, that current may be maximum current or minimum current. The actual current may be lying between minimum current and maximum current. So actual current flow is the actual current is equivalent to flow of an edge. Okay. So of course this flow has to be less than or equal to the capacity in this case, right? The capacity is the maximum current. So that is the thing. So that means capacity represents the impedance, minimum impedance or maximum impedance, whatever, based on the minimum impedance. So this is the physical interpretation with an example in using electric circuit, electric network. Okay. So now coming back to the network concept here. A flow in a digraph, that is directed graph, G equal to V comma E. Okay, the flow is a real value function. Okay, function is supposed to map one domain to range. The domain is uh, okay, R such that the following conditions are satisfied. So that is the thing. So what is the meaning of a flow in a network? So flow is defined like this, defined as a mapping from a Cartesian product V cross B V cross V means basically it is representing an edge. It is representing an edge. So are you getting my point? V cross V.
Sir, are able to
Set
repeat for me?
dimension to.
For example, let's say V equal to let's say 1 comma 2. Two vertices are there, and the vertices are labeled as 1 and 2, vertex 1 and vertex 2. Now, if I want to compute V cross V, okay, so then what will be V cross V? V cross V, কি হবে?
So 1 cross 2.
No, not. It's at a Cartesian product of two sets. So one set is V equal to 1 comma 2, another set is V equal to 1 comma 2. So I'm writing again here. So V equal to 1 comma 2, right? So given these two sets, identicals, when the same set, we are doing Cartesian product on the same set, V equal to 1 comma 2. So then what can we write? What will be V comma V? V cross V. So that is 1 comma 1. First of all, yes, and then 1 comma 2, and then 2 comma 1, and then 2 comma 2. Correct?
Yes, sir.
Okay. Now, in this V cross V, okay, so what we are doing, we are basically, in other words, what we can say that it is actually a set of pairs U comma V, right? So what we are doing, it's a set of these first brackets. And what are these? These are actually pairs. So this is a set of pairs. And pairs of what? Pairs of vertices. So this set is nothing but a set of pairs of vertices, vertex pairs. And what do you mean by a vertex pair? What do you mean by U comma V?
Edge.
Edge. So this is a set of edges. Okay. So such that U U comma V belongs to capital V. Okay. So that is the case. So what you are doing, all the possible edges present in that graph, you are actually mapping all those edges to some sort of a real value. What do we mean by that? So that means you are actually, in this, for example, this case, you are applying some function f, okay? That f is applied on each of these edges. This dot means each of these edges. So first this edge, you are getting some value. Then this edge, you are getting another value. Then this edge, you are getting another value. And then this edge, you are getting another value. So each of the edges are now converted into a single real value by applying this function f. Let's say this is 2, this is 1, let's say this is 3, let's say this is 2. So this function, or this function is actually known as the flow value. Whatever we are getting, this function is called flow, and this is the flow values, amount of flow. So these are actually the amount of flow, or simply you can call them as flow. Mathematically, the function is flow, and this is the flow value, and always, and we normally, usually, we say that these are the flow values, or simply flow. What is the flow of an edge? These are the flows of these edges. That is the meaning of a flow in a network. Okay. So this is an example. such that the following conditions are satisfied. Now, what are the conditions? The conditions are like number one, the flow corresponding to an edge u comma v, which is denoted by f of u comma v, it has to be less than or equal to the capacity, which we have convinced ourselves with the help of an example, right? The flow is less than or equal to capacity in this case, because capacity is the, I mean, the maximum current which can flow along a branch, and flow is the actual current flowing through that branch. So flow is of course less than or equal to the capacity of an edge, and capacity of an edge is denoted by small c of u comma v, and this is known as capacity V. And next point is, next condition is, okay, in a directed graph, because it is depending on the direction, it is equivalent to actual current flow. So current does have a direction. So flow is equivalent to have a direction. So the value of flow of an edge u comma v means the flow from vertex u towards vertex v. So what do you mean by f of ub? So this is a vertex, this is another vertex, this is vertex u, and this is vertex v. And the amount of flow or equivalent to current is actually f of uv. Okay, so this is the meaning. So it depends on the direction. But if I want to have a flow from vertex V to vertex U, the magnitude is same, but to represent the direction, we have to put here minus f of v comma v. And this is a symmetric property. Okay. Number 3 is it is based on Kirchhoff's current law, KCL. The amount of current converging into a single node should be equal to the net amount of current diverging from that node, right? That is the KCL. Now, similar as flow is equivalent to actual current flow along a branch, so similar principle we can apply. That is, the sum of all flows, okay, converged. It is okay. Let's say U is the vertex from where all the flows are outgoing. So U belongs to P. So for all the vertex, the amount of flow okay, pictorially it means, right? So we can think like this, okay? So let's say this is the incoming flow. So there may be many edges. So this is, let's say, for all U, for all, okay. So for all U, V is fixed. So that means this can't be U. So this is fixed. So this is V. Okay, so this is V. This is V. And there may be many U. This may be U. This may be U. Okay, so that means you can have many edges. And directions are like this. Directions are like this. Okay, So what you are doing, you are summing up all the flows converging into the vertex V for all vertex U belongs to V. This is the meaning of this summation. Summation of all the flows, flow of this edge, which are converging to the vertex V. Have you understood now? Have you understood?
Yes, sir.
Okay. So this is that this is the incoming flow onto a vertex V from many other vertices U belongs to capital V. And that should be equal to all the outgoing flows, from that vertex V, like this.
Sir, আপনি এখানে KCL লাগালেন?
Yes, KCL. This is actually based on the KCL, Kirchhoff's current law. Okay, so this is summation of f of v comma w. So all the flows outgoing from vertex V. So V is fixed. That means for all W belongs to capital V. Is it now correct? Why it is W belongs to V and why it is U belongs to V? So this is the representation. Okay, and here what we are doing, it is the conservation principle. The flow is being conserved. Net incoming flow is equal to net outgoing flow. So this is the conversion of flow principle.
Sir, conservation হবে না?
Conservation.
কনজারভেশন হতে পারে, আবার কনভার্সনও বলতে পারে। কনজারভেশনও বলে দিতে পারে, এটা সুবিধা। কনজারভেশন, ঠিক আছে না? কি হবে?
Yes, sir.
Okay, so these are the three conditions to be satisfied, and this is the Q symmetry. Okay. So all these three conditions to be satisfied. So then only you can define a flow of an edge in a graph G equal to V comma E. Any question up to this? Okay.
Sir, এই প্রপার্টিটার নাম skew symmetric property.
Skew symmetry. Symmetry is something f of u comma v is equal to f of v comma u, not minus.
Okay, sir.
Oh, বানানটা ভুল আছে না?
Sir, W হবে।
Okay. Okay. তোমরা খাতায় লিখছো? যেটুকু দরকার।
হ্যাঁ স্যার।
নাহলে কিন্তু বুঝতে পারবে না। আমি এতে পড়াচ্ছি মানে একটু স্লো হয়ে যাব, কিন্তু স্লো হলে তোমরা একটা সুবিধা হচ্ছে তোমরা ভালোভাবে ডাইজেস্ট করতে পারো। এখনই হ্যান্ডস অন করে খাতায় এঁকে এঁকে তোমরা এখনই বুঝে নিতে পারবে প্রবলেমটা কিভাবে সলভ হবে। বাড়িতে আর সেলফ স্টাডি করার দরকার। Okay, so the blue color labels, what are those? These are capacities of the edges. ঠিক আছে? Okay, so this is a flow network. This is an example of a flow network.
স্যার ওগুলো কি 0/2 লিখেছেন?
Yes.
আচ্ছা আচ্ছা।
Okay, so any value, any labeling, let's say 1/3, it denotes the flow is 1 with the capacity 3. Okay, so that means here any level is flow by capacity. In that basis the levels
স্যার এখানে তো ক্যাপাসিটিটাই তো মানে মানে কস্ট গুলোই তো, মানে ওয়েট গুলো।
Yes, you can say so. The capacity are the costs, the maximum costs.
Yes.
But I mean, as now we are actually considering about the flow, that means in real time, okay, I mean in the transient condition, the costs are changing. Whatever path you are selecting based on the you are considering flow as also costs. So there will be an actual cost and the maximum cost. So better we understand now onwards that flow is something actual value which is flowing along, propagating through a branch, and capacity is the maximum amount of flow that can be propagated through a branch. That is the thing. It can be cost, it can be some current. Okay. Now, okay. Now, can you verify is this a flow network or not? That means, can you verify that all the conditions are satisfied? The three conditions. What are the conditions? First is all the flow, any flow in an edge should be less than or equal to C u comma p. Here more specifically it is okay, and flow. No, sorry, my mistake. It should be applied over here. Okay, so where capacity has to be a positive quantity greater than or equal to 0, but you may arise to some confusion. Okay, there exists some minus of f. So how can, but still it has to be less than or equal to c of u comma p. Okay, so flow. I mean, can you verify this capacity rule, skew symmetric property, and conservation of flow principle in this flow network? Then we can conclude that it's a flow network and all the flows are valid. Please verify, check. S is the source vertex and T is the destination vertex. Or sometime in graph theory, this S actually called source, only source, and this T is called sink.
স্যার বলছি ইউ আর ভিটা কি ইউটা সোর্স আর ভিটা ডেস্টিনেশন হিসেবে ধরতে হবে?
Under UV, now that is true for any vertex.
আচ্ছা আচ্ছা, হ্যাঁ ওটাই জিজ্ঞেস, ওকে। তাহলে স্যার সেকেন্ড প্রপার্টিটা ভেরিফাই করা যাচ্ছে না।
You can apply, you will apply that flow conservation principle for all the vertices excluding S and T. So here it is applicable for all, you know, V belongs to, I forgot to mention, V minus S and T, where S is source, S is the source and T is the sink. The flow is always directed from source to sink. Okay, so that is the concept. কি বলছো?
স্যার বলছিলাম সেকেন্ড যে প্রপার্টিটা আছে ওটা তো ভেরিফাই করা যাচ্ছে না বোধহয়।
ওটা এখানে কোথাও লাগছে না অ্যাকচুয়ালি।
হ্যাঁ স্যার ওটাই বলুন।
হ্যাঁ, ওটা আমার কোনো ওরকম কোনো আমার প্যারালাল এজেস নেই, আছে কি?
স্যার সিঙ্কটা কি স্যার? ওখানে কি ডেটা লস্ট হয়ে যাচ্ছে?
সিঙ্কটা হচ্ছে টি, এই ভার্টেক্স টিটাকে সিঙ্ক বলে, এসটাকে সোর্স বলে।
স্যার এখানে ডেটা লসের কিছু পেপার আছে নাকি? এই জন্য বলছি।
হ্যাঁ, কি বলছো?
ডেটা লসের পেপার আছে নাকি?
ডেটা লস তো হচ্ছে না এখানে, তোমার ফ্লো যদি একটা ডেটা হয় তো ডেটা রিজার্ভ থাকছে।
ওকে স্যার।
Okay, so that is the thing. Now flow network we have understood. Now what is our job in this course? What we are supposed to solve? We want to solve a problem. Okay, so given a flow network, we want to find an optimal flow. Means in this case actually it's a maximum flow, it's a maximization problem from source S to sink T. There are many paths available, right? You can find many paths. Let's say S A B T, then S A C D T, S A C D B T. Okay, also S C D T, S C D B T. There are many forward paths which you can find from source to sink, and out of which you can find the optimum flow, means that path which yields the maximum flow from source to sink. So that's a maximization point. Okay. Now optimal flow, so let's now try to understand the flow of a network. So we have now understood flow corresponding to each edge, and now we will understand flow of an overall graph, overall network. So flow of a network, and that is defined as so F is equal to the summation of all F from source to U for all U belongs to capital T. So you are outgoing from, you have started your journey from S, and you are finding all the possible edges adjacent, connecting S. In this example, you can find two edges. One is S comma A, another is S comma C. Am I correct?
Yes, sir.
Okay. So you, according to this formula, you can have two edges, S of S comma A and S of S comma C. And what are the flow values? That is S comma A, f of S comma A is 1, f of S comma C is 1. So it is sum of them is equal to 2. And flow of a network means overall network is now defined as the summation of all those outgoing flows from the source. That is 2. So flow of this network, example network is 2. That is the definition. And in fact, as the third property, that is the conservation of flow is maintained, okay, so you can prove that this will be eventually sum of all the incoming flows to the T, sink T. That means some W comma T, okay, where W belongs to all vertices. W belongs to the vertex at capital T. So this is the outgoing, net outgoing flow, and this is the net incoming flow. So you can see that what are F, W, comma T? That is one edge is B, comma T, another is D, comma T, and their flows are 1 and 1 respectively, and sum of them is equal to 2. So from the principle of flow conversion, we can actually define flow of an overall network. Flow of a directed graph, okay, is defined as the sum of net outgoing and sum of equal to sum of net incoming flow. Too simple. ঠিক আছে? Any doubt? Okay. Now residual network. Okay. It contains the same vertices of G equal to V comma E. That is the network, original network. Okay. And one or two, it is for each. It is very interesting concept, residual network. This concept will be used in an algorithm to find the maximum flow, which is the augmenting path algorithm. Okay, so one or two edges, for each edge, U comma V in the original in the G in G in G. Okay. So satisfying the following properties, or not properties, following rules. Okay, so number one, what are the rules based on which you will form construct a residual network? Number one is, if a flow of an edge f of u comma v is flow of u comma v is less than or equal to the capacity. It can be less than capacity or it may be equal to the capacity as per the first condition, right? First property, the capacity rule of any flow can be equal to the capacity, or it can be strictly less than the capacity, or it can be equal to the capacity. So there are two possibilities, and based on those two possibilities, we will have two different rules. So if it is strictly less than the capacity of C of u comma v, u comma v, then there will be a forward edge u comma v with capacity u comma v as the existing capacity C of u comma v minus the flow. Okay. And next, number 2, if f of u comma v is greater than 0, it can be negative, but if it is positive, then there will be a backward edge v comma u with capacity Cf equal to the flow. Cf u comma v equal to the flow. Okay, so let's take an example, otherwise it will be difficult. So we can actually take the same example, this one. এরপরে তোমাদের কি আছে?
স্যার ল্যাব।
স্যার ল্যাব আছে
তাহলে এখানেই শেষ করতে হবে।
4টে থেকে।
স্যার ল্যাব প্লাস।
So consider this example. I'm just showing one or two examples, and in the next class we will elaborately find residual network of that graph G, of this graph G. One or two, this just to make you understand about the rules, so that you can do the rest. If consider any edge, let's say S comma A. That is the edge, S comma A, and what its flow 1. The question is the flow is strictly less than the capacity? That capacity is 3. Is it satisfying with rule 1? Yes. So then
Yes.
what we are doing, we are actually introducing a forward edge with the capacity. And what will be the new capacity of this path, of this new edge, forward edge? Its capacity Cf will be the existing capacity minus the flow. Then what will happen?
2.
2. Okay, so that is 2. And then is it greater than 0? Is the flow greater than 0?
Yes.
Yes, sir.
So there will be a backward edge. Like this, and its capacity will be the existing flow, that is 1. That is the meaning, and we will erase this. That will be the ultimate picture when applied these two rules onto this edge S comma A. So you iteratively apply these two rules to construct the residual network of the overall
Sir.
flow network. Yes.
স্যার অ্যাকচুয়ালি এটা 3টা ডিভাইডেড 2r প্লাস 2r 1 হলো, তো মানে ম্যাক্সিমামটা ডিভাইড হয়ে গেল।
Yes.
আচ্ছা আচ্ছা।
Okay. So you now you can apply. I think now you can apply these two rules to iteratively on all the remaining number of edges in the flow network, and find the residual. So this is the part of the residual network, and you apply these rules onto all the edges, all the other edges, and draw the red color forward edges if there is any possible, and the purple color backward edges if there is any possibility, and remove the existing black colored edges in the original. Whatever you will get the network, with the forward edges and backward edges. That is the residual network of this original version. And residual network is usually denoted by capital G with suffix F. So this is the part of the GF. When you apply, you will get the overall GF. Anyway, I will stop here and I will আমার মনে হয় তোমরা করতে পারবে। নেক্সট দিন আমাকে কেউ একজন দেখিয়ে দিও তাহলে।
স্যার একটা বিষয় স্যার, যদি ফার্স্ট ইফটা না স্যাটিসফাই করে তাহলে কি সেকেন্ড ইফটায় যাবে?
ইফটা না দুটোই এক্সস্টিভ, ঠিক আছে? একটা করলে আরেকটা অ্যাপ্লাই করা যাবে না তা নয়, তুমি দুটোই অ্যাপ্লাই করো।
আচ্ছা
অল দি এজেস। তুমি হয়তো কোনো ক্ষেত্রে মানে ফার্স্ট এডটা পেলে না, বাট সেকেন্ড এডটা পাবে। সো ফরওয়ার্ড এজটা তুমি নাও পেতে পারো, কিন্তু ব্যাকওয়ার্ড এজটা কিন্তু পেয়ে যাবে সেক্ষেত্রে।
আচ্ছা, ওকে স্যার, ওকে।
এবার যখনই তুমি দেখবে, এটা একটা ভেরি ইন্টারেস্টিং কনসেপ্ট, যখনই তুমি দেখবে রেসিডুয়াল নেটওয়ার্কে, রেসিডুয়াল নেটওয়ার্ক না তৈরি করতে পারলে তুমি নেক্সট দিন যেটা আলোচনা করবো অগমেন্টিং পাথ খুঁজে পাবে না। তো যেখানে আমি বললাম যে এখানে অনেকগুলো পাথ অ্যাভেলেবিলিটি রয়েছে সোর্স থেকে সিঙ্কের দিকে, তাহলে তোমাকে তার মধ্যে একটা ম্যাক্সিমাম ফ্লো পাথ বের করতে হবে। কিন্তু আমি যদি রেসিডুয়াল নেটওয়ার্ক অ্যাপ্লাই করি তাহলে দেখবে অনেক পাথ মানে ফরওয়ার্ড পাথ আর পাওয়া যাচ্ছে, যেখানে যেখানে যে এজগুলোতে ফরওয়ার্ড এজ নেই কিন্তু ব্যাকওয়ার্ড এজ আছে, হতে তো পারে ফ্লোটা ইকুয়াল টু ক্যাপাসিটি, সেক্ষেত্রে ফরওয়ার্ড পাথ এজ থাকবে না, শুধু ব্যাকওয়ার্ডটা থাকবে। তার মানে কি, তুমি যখন পাথটা সোর্স থেকে সিঙ্কের দিকে যখন মুভ করার চেষ্টা করবে, তখন তোমার কাছে কোনো এজে রেসিডুয়াল নেটওয়ার্কে তোমার ফরওয়ার্ড এজটা না থাকার জন্য ওই এজের থ্রু দিয়ে তুমি আর যেতে পারছো না, স্টপ হয়ে যাবে। দ্যাট মিনস ওই পাথটা তোমার রিজেক্ট হয়ে গেল। দ্যাট ক্যানট বি that path cannot yield maximum flow.
Yes, yes.
That's why. So this is called an augmenting path algorithm. যেটা আমরা নেক্সট আলোচনা করব। ওকে, আজকে ডেট হচ্ছে 28। সৌমার্থ
প্রেজেন্ট স্যার।
স্যার আজকের এই নোটস একটু দিয়ে দেবেন?
হ্যাঁ, যাদের হয়ে যাচ্ছে একটু জয়েন করে নাও।